This is part 5 of week 3, conservation laws. Let's get going. So we have discovered notion of linear momentum, conservation of linear momentum. We spoke about the notion of kinetic energy, potential energy, and more generally energy. And I made the statement, without really giving you a proof, that energy is a quantity that is always conserved. Sorry, conserved. So it means that sometimes energy is transformed in other forms. So if you have kinetic energy, you can transform this kinetic energy into gravitational potential energy, or in spring potential energy. But it also means that sometimes this energy can be transformed into other forms of energy. So what are these other forms of energy? There are several. We can readily identify chemical energy, the energy in the fuel of your car. You go to the service station, the gas station, to get fuel, and this fuel now is used inside your engine. So the fuel is exposed to oxygen, the oxygen of the air, with a spark, and so there's a chemical reaction between the fuel and the oxygen. This chemical reaction releases, transforms the matter which is there and produces a gas at high temperature, high pressure, and this gas then is what propels the pistons of the engine, and those pistons activate all the machinery of your car, the crankshaft, and then this is connected to the transmission, and the transmission then makes the wheels of your car spin. And so it's a case where chemical energy, the energy stored in the fuel that you put in your car, is then transformed into mechanical energy, that is the rotation of the wheels of your car. Yet another example is what we have today, hybrid or electric cars. So in an electric car, you have a battery, and this battery stores energy in the form of charge, or an electric charge. And then you can use this electric energy to activate an electric motor, and which means that electric energy stored into the battery will then be converted to produce mechanical energy of the wheels of the car, and then the motion of the car itself. Right? There's also nuclear energy. So the nucleus of atoms can undergo reactions, so-called nuclear reactions, and the energy of the nucleus then can be exploited to release actually a vast amount of energy that can be transformed or converted, for instance, to heat water, generate vapor. This vapor then can be used to mechanically activate a turbine, which in turn spins an electric generator that produces electricity, and then this electricity is sent onto the wire to your house, to your home. There's yet another form of energy, which is known as internal or heat energy. Which is that in the wherever you might be sitting or studying, the room is at a certain temperature. And temperature means that the molecules of the air around you are moving constantly, evidently so fast and so small that you cannot see them with just with your eye, but one can actually reason and calculate what is the velocity of these molecules, and one find that they have a random motion at a velocity that depends on the actual temperature in the room. There's yet a form of energy that is not mentioned here, a so-called radiant energy. So light, for instance, heat, infrared radiation is a form of radiation that can propagate through space, through matter, and so on and so forth. Now, in general, one form of energy, mechanical energy, can originate from another form of energy, chemical energy or electrical energy. One can also use mechanical energy to store chemical energy or electric energy or nuclear energy or gravitational energy and so on and so forth. So there are many ways of transforming one type of energy into another, and sometimes it's possible to transform back. In the process of converting and transforming one type of energy into another, there's always a loss of some kind, and this loss is not a loss of energy. It's a transformation. It's a transformation of part of the energy that was converted into what we call heat. And this transformation into heat, what you feel, for instance, when you rub your hands, the heat, the increase in temperature that you feel when you rub your hands very, vigorously, this is happening due to friction. So mechanical energy is dissipated, transformed into heat, and that's due to friction. The energy is transformed, but it's not lost. You can always account for where the energy goes. So if you have electrical going into mechanical, but not all of it is transformed, some of the energy will be going into the production of heat. And this is typically possible to visualize or observe just by measuring the change of temperature of the object or the phenomena or the things involved in a particular phenomenon. So let me give you these two tables here, examples that is good to be familiar with and to understand what type of energy is converted into what type of energy here. So for instance, if you have a car engine using fuel, one uses the chemical energy to produce mechanical or kinetic energy. And so think about the others for yourself. Then let me ask you, if you have a battery, whether it's a battery in your car or a battery in your computer or a battery into some toy, what form of conversion is taking place? I'll let you answer that. Well, when you use a battery, the first conversion that takes place is chemical energy into electrical energy. Evidently, you can now use this electrical energy to do something else. The something else could be the activation of a motor, which would then transform the electric energy into mechanical energy or kinetic and generate kinetic energy. Right? That's one option. Energy is always conserved. So if you have a car coming to rest, the kinetic energy of the car is now gone somehow. It has been dissipated. And typically in traditional cars, the kinetic energy will be dissipated by friction using brakes. So the brakes of a car involve a surface on which you apply a pad, and you press the pad onto the metallic surface, and as you put pressure, this generates friction, and it is this friction then that slows down the car, which means that in practice, the kinetic energy of the car is dissipated into the heat generated by this friction. Right? Now, if you think about this, as you drive your car day in, day out, and you accelerate and decelerate, when you decelerate, in general, you're using the brakes. So that means that you end up dissipating a lot of heat, a lot of kinetic energy into heat. So that means that the pads of your brakes are subjected to a lot of heat. So if you take a substance and you repeatedly heat it, it will have a tendency to want to evaporate. Pads of cars are made in substances or materials that don't readily evaporate. They are materials that are really resistant against rising the temperature, against heat, the presence of heat. But over time, they nonetheless will lose, and they will lose some of their mass, and they effectively then will lose their effectiveness, and they will eventually not work very well anymore. So consider another example, that of a ball that was, let's say, released from some height. The ball accelerates, it bounces off the ground and comes back up. You might have observed yourself that in general, the ball never comes back to the same height at which it was released. Very elastic ball will rise almost to the same point. For instance, if you use a good basketball, well, inflated, you let it down, it will come back almost to the same height, but not quite the same, right? So potential energy is converted into kinetic energy to go down. Kinetic energy is converted into potential energy to go up. But some of that kinetic energy doesn't go into potential energy. It goes into the compression of the ball, which leads to internal losses or internal energy of the ball. So if you do this repeatedly, you will see that the basketball or other ball that you might be using, you will see that the ball is rising slightly in temperature as you do this. Another example of conservation of energy is the energy generated at power plants. Power plants can generate energy from a variety of ways, by burning coal, by burning fuel, by activating turbines with falling water, and so on. But in general, you will find that a power plant always has to produce more power than what it can provide to the consumer. And that's because the very process of producing this power will have some wastes or will have some losses. The losses can happen within the power plant itself, but in general they will also apply in the network used to distribute the power. So the wires that we use to transmit electrical power don't transmit power without this electricity, without losses. There is actually a loss of energy for every kilometer traveled by the electricity. So, and this is something that one can actually understand and calculate very well today. Let me give you a specific numerical example. A person driving a 2,000 kilogram car moving at 10 meters per second, and this person then decided to take their foot off the gas pedal and then apply the brakes. The car comes to a stop in 10 meters, and so you can ask, what is the work done by friction to stop the car? So you go from 10 meters per second to 0, in 10 meter. What is the work being done to stop the car? So you need to calculate the force and you need to calculate the work. I'll let you think about it for a moment. The work is negative. Why is the work negative? The work is negative because you had to slow down the car. So that means that the displacement is in one direction, but the force is in the other direction. So you are decelerating the car, so the acceleration is in a direction opposite the velocity of the car. So at the end of the day, we can say that energy is always conserved. Energy is always conserved, but it can change form. Kinetic energy, however, is not always conserved because losses may happen. And that means that part of the kinetic energy may be converted into other forms, and particularly into the production of heat. Now, in general, when we deal with collisions in particular, there will be collisions that are said to be elastic because they conserve kinetic energy or nearly conserve kinetic energy, whereas there are, in general, collisions will be said to be inelastic because they do not conserve kinetic energy. So let's consider an example that we've already actually discussed, that of the 10,000 kilogram truck traveling at 12 meters per second hitting a 2,000 kilogram car standing at rest. We saw that the truck hits the car is then set into motion, and the truck is seen afterward to be moving at 9 meters per second after the collision. And so the car is moving at 10 meters per second, as we already saw. We saw that the kinetic energy goes from 720,000 joules to 630,000 joules. And we said, well, the missing energy is going into, basically it's transformed. You are bending metal. You are bending chassis and body of the truck and cars. So you are then transforming this kinetic energy into the internal energy of the fenders and chassis of the truck and car that you're smashing and squeezing. Another example, a car of mass m traveling at v1 equals 10 meters per second collides with an identical car, same mass, standing at rest, v2 equals 0. They undergo an elastic collision. What is the outcome of the collision? The key word is elastic collision. You know that momentum is conserved. That's always true. Elastic collision means that kinetic energy is also conserved. So the first car will stop in the second, will start moving with a v equal 10 meters per second. This conserves both momentum energy because mv1 equals mv2 and 1/2 mv1 square equals 1/2 mv2 square. v2 square after the collision. Now, in general, collisions are rarely elastic, right? Most of the time, most collisions tend to be quite inelastic. So it's interesting to then consider problems involving phenomena that are not elastic. But let's start with a phenomenon involving elastic collisions. So let's say a very elastic ball is thrown at a wall of a building at velocity of 10 meters per second, plus 10. So it's going to the wall. If both energy and momentum are to be conserved, what should be the velocity of the ball after the impact? Well, the wall is not moving, and the wall will then impart an impulse onto the ball, and so the ball will come back out of the wall with the same velocity, the same exact velocity. This will conserve kinetic energy as well as momentum, because there will be an impulse given onto the ball, and then this is something that you can also think about and review in your textbook. And I will stop here again. And after this, we will see yet another section of this chapter.